Hi everyone, welcome to part 4 of our series on understanding the convergence of infinite sums. Today we're going to be focusing on two tests, the ratio test and the root test. Now I can't think of a cool title for this one, like reimagining the infinite series or anything like that. So this is just going to be ratio and root test. Sorry about that. If you think of a good title, let me know. But yeah, let's go ahead and get started. So starting off with the ratio test here. So the ratio test, it's kind of like when we did monoticity with sequences, in that we used a ratio to tell whether or not the sequence is going to strictly increase or strictly decrease. This time, we're going to be doing that but with infinite sums and a limit. So, the rule for the ratio test, we're going to let some value L equal the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. And notice that we're going to deal with these absolute values a little bit later when we get to absolute convergence. For now, just leave the absolute values as is. Just trust the process here. So, with this limit as n goes to infinity of a sub n plus 1 over a sub n, you can tell that we're dealing with terms that are infinitely far away in the sequence. And this L right here represents a scalar multiple. If I went ahead and multiplied this limit on both sides for limit as n goes to infinity of a sub n, you would notice that we get the limit as n goes to infinity of the absolute value of a sub n plus 1. This is equal to L times the limit as n goes to infinity of the absolute value of a sub n. And so here's the thing. This has three specific outcomes. So we can say that if L is between 0 and 1, 0 included, then the series of a sub n converges. However, if L is greater than 1, then that means that this is strictly increasing as the limit as n goes to infinity of a sub 1, that n plus 1 term of a sub n, sorry about that, is going to be larger than the a sub n term, than the nth term of a sub n by a factor of L. So that means it's going to be increasing at a factor of L, and we don't want that because that'll mean that the series diverges, and that's kind of the sad ending here. But the even sadder ending is that if L equals 1, because if L equals 1, then this limit equals this limit. So that means that this limit could be 1, and then we would just be adding on a bunch of 1s forever and ever, or this limit could be 0, and we just add on a bunch of 0s forever. So we won't know if it converges or diverges. So then this series right here, or this result, is inconclusive. Yeah, I spelled that right. Inconclusive, and whenever it's inconclusive, we put a sad face. So, let's go ahead and get into some examples here. We have the series from 1 to infinity of n squared over 3 to the n times n plus 1. So let's go ahead and try using the ratio test. So we have the limit as n goes to infinity, the absolute value of a sub n plus 1. Since we have a sub n plus 1, we replace all the n's with an n plus 1. So this becomes n plus 1 squared over 3 to the n plus 1 times n plus 1 is n plus 2. And now notice here, I don't really have space to write the bottom fraction, so I'm going to multiply it by the reciprocal in one step. So by multiplying by the reciprocal, this 3 to the n times n plus 1 goes on top. So you get 3 to the n times n plus 1 divided by n squared. So now take a good look. If you're looking closely at this, we have a 3 to the n on top and a 3 to the n plus 1 on the bottom. Therefore, we can cancel out a 3 to the n in both the numerator and the denominator, but as a result, we'd just be left with 3. And I'll go ahead and draw this out to the side here. We have 3 to the n over 3 to the n plus 1. 3 to the n plus 1 is equal to 3 times 3 to the n. Therefore, we just have a 3 in the denominator there. So, therefore, we just have a 1/3, so we can go ahead and leave that outside. 1/3 times the limit as n goes to infinity of n plus 1 squared times n plus 1, which is n plus 1 cubed, divided by n squared times n plus 2. Now notice here, although it may not look like it at first glance, this n squared times n plus 2, this is equal to n cubed plus 2n. And in this case, we have n plus 1 cubed. So both the leading coefficient, both the degrees for the numerator and the denominator are 3. So this is just n behavior of rational functions, and we just take the leading coefficient. So we have 1/3 times 1 over 1, which is just 1/3. So 1/3, since that's less than 1 and greater than 0, we say that this converges, and we just write ratio next to it because it's by the ratio test. So, moving on to the next example here. We have a series from 1 to infinity of n to the n divided by n factorial. And you can kind of tell, based on the order of magnitude, that this n to the n is going to outgrow this n factorial, so you know it's going to diverge. You could put that, but for the sake of this video, we're going to use the ratio test to prove it. So let's go ahead and get started here. We have the limit as n approaches infinity of the absolute value of a sub n plus 1, which is going to be n plus 1 to the n plus 1 power. Make sure you put both n plus 1s in for both of the n's. That is a mistake that people make. And then we divide that by n plus 1 factorial, multiplied that by n factorial over n to the n. And if you notice here, n plus 1 factorial, this is the same as n plus 1 times n factorial, based on the definition of the factorial. So, since we'll have an n factorial in both the numerator and the denominator, we can cancel out that n factorial, and we'll just be left with the n plus 1 in the denominator. So, as a result, we can go ahead and do another cancellation here. Notice that we have an n plus 1 to the n plus 1 divided by an n plus 1. So n plus 1 to the n plus 1, that's the same as n plus 1 to the n times n plus 1. I'll go ahead and write that out here. So you have n plus 1 to the n plus 1. Again, that's just n plus 1 to the n times n plus 1, based on exponent properties, not probabilities. Sorry about that. So, notice here, we have an n plus 1 just out by itself, and then we have an n plus 1 on the bottom. So, this n plus 1 cancels with the remaining n plus 1, and we'll be left with an n plus 1 to the n. So that was a bad cancellation on my part. So, as a result, we'll be left with the limit as n goes to infinity of the absolute value of n plus 1 to the n over n to the n. And we can go ahead and combine these exponents into 1, giving us n plus 1 over n to the n. And we could do one last manipulation here and split up this fraction into 2, giving us the limit as n goes to infinity, the absolute value of 1 plus 1 over n to the n. And this form is actually a really familiar limit in calculus, as this right here is the limit definition of E. And E is approximately 2.718. And 2.718, that's greater than 1. So therefore, we say that this series diverges by the ratio test. And that's it. Those are 2 examples of the ratio test. There are obviously more examples out there, but these 2 pretty much summarize the convergence and divergence of the ratio test. So let's move on to the root test. So the root test, it's pretty hard to explain what goes on conceptually, so I'm going to do a full-fledged mathematical proof here. So, again, we're going to let L equal the limit as n goes to infinity, but this time it's going to be the absolute value of a sub n raised to the 1 over n power. This is the equivalent form of the nth root of the absolute value of a sub n. Notice that. So, we're going to define L to be a positive limit result, 0. And we're going to choose some value r such that r is greater than this limit L. So, notice here, what we're going to do is we're going to kind of change out this, this expression here. We're going to ignore this limit for now. So we're going to say that a sub n to the 1 over n is going to be less than r. So then, if we go ahead and take both sides to the nth power, this 1 over n power will cancel with the n, giving us the absolute value of a sub n is less than r to the n. So then what we're going to do is we're going to say that if we take the summation of 1 to infinity of r to the nth power, we know that this is a geometric series. So we're going to say that this series converges if the absolute value of r, not the absolute value of r, if 0 is less than or equal to r less than 1. And notice, we're not going to deal with absolute value of r less than 1 because we're not dealing with negative numbers here for r. Remember, we defined L to be greater than 0. So, if this series converges, we know that this sequence a sub n is less than r to the n. So by the direct comparison test, this series from 1 to infinity of r to the n will also converge if, not r to the n, of a sub n, absolute value of a sub n, converges if, again, 0 is less than or equal to r less than 1, and this is by the direct comparison test. Now notice, we defined L to be less than r. If we define L as less than r, then this L will also have to be less than 1. So we can pretty much say that this series will converge if 0 is less than or equal to L, which is less than 1. And the thing is, with this test right here, it follows the same rules as the ratio test. If r is greater than 1, if L is greater than 1, then that means that this series will diverge. And if L is equal to 1, then it's, again, inconclusive. And you can do the mathematical proof again with this geometric series right here. We know that if this r is greater than 1, then this will diverge, and then this will also diverge. But obviously, again, DCT, it's a little bit more complicated than that. But that's the fundamental idea. So we're going to go ahead and get started here. So we have the series from 1 to infinity of 3 to the 2n plus 1 divided by n to the n. And you can already tell if this series is going to converge, but let's use the root test to prove that. So we're going to go ahead and say that we have the limit as n goes to infinity of the absolute value of 3 to the 2n plus 1 divided by n to the n to the raised to the 1 over n power. And let's go ahead and rewrite this just so it's a little bit easier to see. This is the same as the nth root of 3 to the 2n plus 1 divided by n to the n. Now this is where exponent properties come into handy, because 3 to the 2n plus 1, this can be rewritten as, again, nth root of 3 times 3 to the 2n, and 3 to the 2n, that's the same as 3 squared to the nth power. So 3 squared, that's 9. So this is 3 times 9 to the n divided by n to the n. And with this root right here, whenever quantity has a power of n, we can take that out of the root, because we have the nth root and then we have the nth power. Again, since that's just 1 over n times n, it'll cancel out. So we have this is equal to the limit as n goes to infinity of 9 over n times the nth root of 3. And notice, if we go ahead and use this, if we go ahead and take the limit as n goes to infinity of the nth root of 3, that's just 1. Because 1 over infinity right here, that's 0. Anything to the 0th power is 1. So we have the limit as n goes to infinity of 9 times 1 over n, and that's just equal to 0. Because 9 over infinity, that's 0. And 0, we know that's less than 1. So this converges by the root test. And notice here, the root test is kind of a more exclusive test, as the root test is really only useful for whenever you have things raised to the power of n. If we had something like factorials, for example, then it might be more appropriate to use like the ratio test, or even the nth term test, or just any term that has a limit and that cancels. So yeah, with that concludes this video on the ratio and root test. With that, also concludes all the positive series. In our next part, we will be discussing alternating series and how there are multiple different types of convergence. But for now, I'll see you in future parts.